also thanks for giving me the opportunity to speak at this seminar. So indeed, I will talk you a bit about a Coulomb drag between holographic strange metals and more in general about multi-layer holographic system coupled by Coulomb interaction. And this is the work that I did under the supervision of Professor Henk Stoff at Utrecht University. And before going to the Coulomb drag, let me give you a bit of an overview of what we are interested in and how do we study them. We're interested in cuprates. The cuprates are just lattice structure made of copper and oxygen, and they are characterized by strong interactions. And the strong interaction among electrons make them difficult to model, and in particular, we have some peculiar properties that is still unexplained today. The most famous one is that they are high temperature superconductor, and in particular, we're now interested in the strange metal phase that is the normal phase of high temperature superconductor as it lives above the superconducting dome of this cuprated material. And there are several techniques that have been tried to understand these strange metals. And one of such technique is holographic duality. Why is it so? Because this holographic duality is a strong-weak duality. So what I mean by strong-weak duality is that we can describe two things, like the same thing in two ways. One is through a higher dimensional gravitational theory, and this should be equivalent to a quantum field theory in one lower dimension. But the nice thing is that when the quantum field theory is strongly interacting, the dual gravitational theory is just a classical gravitational theory. And the classical gravitational theories are easy, and so we can try to understand a lot of the properties of, or some of the properties of strongly interacting system by looking at these classical gravitational theories. And in particular, as a condensed matter physicist, we use a so-called bottom-up approach. So we try to look at some gravitational theory that is dual to some condensed matter strong interacting theory that reproduces some of the characteristics of the system we are interested in. And one peculiarity of this approach, like where it really shines, is that it allows us to compute the low energy response of systems at both non-zero temperature and non-zero density quite easily. So you can think about it as basically a tool to write down an effective field theory of a strongly interacting condensed matter system. And it is still in use because it has been quite successful in reproducing some of a famous strange metal behavior of a cuprate. Like one of the most famous is the linear interior resistivity that can be included in this holographic model. And one other characteristic of cuprate strange metal that has been observed in ARPES experiment is that seems to have an electron self-energy that is dominated by the frequency dependence. And this is something that occurs quite naturally in a class of holographic systems. So this is why we try to use holography to study the behavior of strange metal. But one peculiarity of this holographic system is that if we study the density response at low energy, we always find a linear mode. And this is quite expected because if you think about it, we are studying a theory with a strong correlation among electrons. So if we have energy and momentum conservation, and in this case, we are taking the simplest case where we have indeed a two-dimensional theory that is isotropic and homogeneous. So we have this momentum conservation, the low energy density excitation will be a linear mode. So what we are describing is this two-dimensional system where a holographic model these strong interactions, but you really have to think about them as living in this 2D plane. So they're not three-dimensional, but they really live in the plane. However, we know that in metals, the Coulomb interaction plays an important role. And so we might expect that at low energy, instead of finding a linear mode, we should find a plasmon mode. So this is a feature that is not present in holography, and people have been wondering how to introduce Coulomb interaction in holography so that together with a strong in-plane interaction coming from the holographic description, we will also have this long-range Coulomb interaction that gives rise to plasmon modes. And in particular, for a 2D system, we can have a three-dimensional typical plasmon dispersion of a 2D system that causes the square root of momentum. And by the way, one thing you can notice here is that we have this Fermi velocity, and also here for the linear sound mode. And of course, the gravitational theory is a relativistic theory, but in order to describe a condensed matter system, we replace C with the Fermi velocity in our computations. Okay, of course, the first thing you should wonder is if it is useful to introduce Coulomb interaction in cuprates. And it turns out to be so because, as you can see, these are some experimental results that are relatively recent for electron dot. This is a layered electron dot cuprate that is basically made of a stack of cuprate layers. And what they observed is that these layers are indeed coupled by the long-range Coulomb interaction, so that this coupling gives a response of the system that contains a so-called acoustic plasmon, that is this linear low-energy plasmon mode. And this is because if you have indeed a strong interacting system that in the neutral case would have this linear response, if you couple a large number of layers, then the response you expect is indeed this acoustic plasma. And what they studied is studying the lifetime of this plasmonic excitation as a function of the out-of-plane momentum, so the moment along this z direction. And it turns out then that if we have a way to introduce these Coulomb interactions in holography, then we can reproduce this acoustic plasmon also in a holographic setting. So what you see here is some numerical computation of a strongly interacting system described by holography. In particular, is a model that has some characteristic of a strange metal. And as you can see, this, what I call pi here, would be the response of a neutral system, the one that contains the linear sound mode. And by introducing this Coulomb interaction in holography, we find an effective potential that gives rise to this linear acoustic plasmon. And this is, of course, this acoustic plasmon depends, as you also saw in the experimental results, on the out-of-plane momentum, that is this P, where L is the inter-layer distance. And well, you could also in principle tune it so that when everything is in phase, we just recover the usual gap, the 3D plasmon mode. Now, of course, you may think that all of this is trivial from a hydrodynamic point of view, because you just have a system with linear sound mode. If you look at the form of the interaction, then it is quite trivial to figure out that the low energy response will be indeed given by this linear acoustic plasmon. But what is not trivial, what holography gives you, that is not in the hydrodynamic description, is the lifetime of this excitation, because this depends on the interactions of a plasma with the quantum critical theory described by holography. And so a non-trivial results from holography would be indeed to be able to compare this lifetime of the plasma. And that is why it is important to introduce this in a holographic setting. And since we notice that...
Sorry, can I just a quick question? Why do you say that lifetime is not in the hydrodynamic description?
Yes, sorry. I should have phrased it better. What I mean is that the lifetime of this excitation is not captured by simple hydrodynamics, in the sense that this lifetime indeed will depend on the particular holographic background, so of the quantum critical theory.
But let's say I know nothing about holography. I'm just asking about the statement at the hydrodynamic level. So why do I say that response function in a hydrodynamic regime does not capture the width of the plasmon peak?
In the sense that, well, I will love that the hydrodynamic description is characterized by some coefficient. So let's say for the diffusive model, I will have some diffusive coefficient E, and then suppose I have this linear sound mode. So this is the diffusive linear sound mode, but will have a lifetime Bs, and these are basically, these I can determine it holographically. So the holography will give me the temperature dependence of these things, so T to some power, while I can't extract them simply by a hydrodynamic model.
I guess I disagree with that. You can. I mean, the question what you are after, I think, at the end. So if there is something very, very special to, I mean, your, I don't know, quantum critical coupling, maybe we can hydrodynamically say what this power law exponent, for instance, would be. But I think hydrodynamic itself is perfectly capable of telling you what the lifetime of the plasmon would be. And in pure hydrodynamic regime, it's just viscosity. Now, if your holography gives you a bit more to say what this viscosity, I mean, scaling as temperature, maybe, but I don't see a connection just yet. So maybe you can explain later.
Yeah, what I mean is that your graphic model will give you the scaling behavior of need of the viscosity and of this coefficient, and then all of these coefficient will follow from there. But the temperature dependence and the general form of these coefficients do depend on the particular quantum critical theory I'm studying, and so they depend on the holographic model I'm considering. And this is where the input of the holographic model comes in. Does this answer your question?
Well, maybe I'll get back to that later. So depending how this, I mean,
okay.
We'll see next, yeah.
And okay, and so we thought, and we have a way of describing a system that is like a multi-layer system that is coupled by Coulomb interaction. We can think maybe about a simple setting that could be checked experimentally. And so we decided to look at the Coulomb drag of two strange metals layer, where again, we have two types of interactions. The strong in-plane interaction will be described by holography, and they only live in plane, so they don't couple the two layers. And the coupling of the layers is going to be given by the Coulomb interaction alone. And in particular, the Coulomb drag, it can be measured in an experiment by taking two layers at a distance L, and we will send a current in one of the two layers that is called the active layer. And then interactions among density fluctuations in the two layers will generate a drag in the passive layer, the one that is not sourced, that will give a potential difference that can be measured, and then we can figure out the drag resistance and its resistivity. So this is what we want to do holographically, and then just to give you an idea of how we can do that, let me quickly show you how what holographic model we use and how things can be done in holography. So we said indeed that is a duality between gravity and strongly interacting in condensed matter theory. So we have an extra dimension that is what we call R here, that defines an energy scale of the theory. And then we have a classical gravitational theory. And in particular, we are interested in a class of theory that are called Einstein-Maxwell-Dilaton gravity theory, where the dilaton refers to this scalar field, because these are characterized by two exponents, the dynamical critical exponent, Z, and the hyperscaling violating exponent. And this allows us to have a theory with time and space scaling differently. And especially, we can find out that the infrared geometry, so we have that our matter theory lives at the boundary where R goes to infinity, while for the small r, we are in the infrared, so the geometry of this gravitational theory at small radius will describe the infrared behavior, so the low energy behavior of our strange metal. And in having these two exponents, we can have then an entropy that scale linearly with temperature, because in particular, we're interested in the solution where the dynamical critical exponent is infinity, and the hyperscaling violating one is such that this ratio is 1. Why is that? Because indeed, we want to describe the strange metal, and this is going to give us a resistivity that scale like entropy, that scales like temperature. And furthermore, we showed that, or at least it's been observed in our past experiment, that indeed the fermionic self-energy is dominated by the frequency behavior, and by having this exponent going to infinity, so that we can have infrared a theory where time scales but space doesn't, and that means that the momentum dependence can only enter in the exponent as it becomes dimensionless, and the self-energy will indeed be dominated by the frequency behavior. So this one of this particular kind of theory that was proposed as a model of a strange metal by Guxer, that has these particular potentials and coupling to a gauge field, is such that it gives us a background. So basically, to explain a bit how things work, from this gravitational theory, we can get the classical equations of motion, and the solution to this classical equation of motion for these fields will characterize the background of our condensed matter theory, the equilibrium background. So since we want an homogeneous and isotropic theory, all these fields that you see here only depends on the radial direction. And in particular, this solution proposed by Gugser support a black hole solution. And this means, from the condensed matter point of view, that we can describe a system at non-zero temperature, because the black hole in the gravitational theory translates to non-zero temperature in the condensed matter theory. And furthermore, we have this gauge field that sets a non-zero density in the dual boundary theory through this radially conserved quantity. So this, what we call n, is the density of the boundary theory. So now we have the equilibrium description of a strong interaction theory with a non-zero density and a non-zero temperature. And if you are interested in studying the response function of this theory, then what we have to do is perturb this equilibrium theory. And by perturbing the classical gravitational action. And from this perturbation, we can basically, since we have that each field is dual to some operator, like the gauge field was dual to a current operator, then we can extract the entire Green's function for all the operators in the theory. And we do that by simply looking indeed at fluctuations of the equations of motion and just studying the solution of this couple set of fluctuations equation that in our case will be for this component of the field, where basically this will give our density response we are interested in. These can only be solved numerically, and once they are solved, you simply look at the boundary behavior and you can extract basically the leading order terms, maybe after the scaling of the field, will give you the source of these fluctuations, and the subleading term will give you a fluctuation of the operator from which we can extract then the response function. And here in the dots, there might be other terms that needs regularization, but these, like we know what to do, we can regularize it at the boundary, and so these terms are not really important for our purposes. And this will indeed give for example, the density response for a 2D system with a strongly in plane interaction, but no dynamical photons, so no Coulomb interactions. And like some time ago, people from a group of Wolfgram at the University of Charles thought about how to introduce how to introduce the Coulomb interaction in holography, and it was realized here in Utrecht and in Leiden that the procedure they were describing was to add a double trace deformation, it's called, because it is double, because it has basically couples the operator in with a, okay, sorry, I'm gonna be confused. For all our purposes, because the term double trace deformations come from a larger limit, and we can neglect it for the moment. What is important for us is that we are coupling a dynamical photon in the boundary to our current operator, that is the one described by our gravitational theory. And you have to notice that this is just a boundary term. So this will not modify the equations of motion. What it will do is that if we look again at the behavior of the fluctuations near the boundary, it will change the boundary conditions, so that now our leading term that was the source will be the source minus these terms that depends on the response as well. And what this does is in turn giving a response function that is this very recognizable form, because it assumes an RPA-like form of a response. So basically what we are doing is that our full response with a double trace deformation will be given by is given neutral response in holography that contains all sorts of strong interactions. And this polarization bubble is resummed in a RPA-like fashion. And then you can easily see that if you have indeed a neutral response with some linear mode, then the addition of this long-range Coulomb interaction that will give an effective potential, it causes 1 over momentum, will give you this plasmonic response function that goes like the square root of Q. Okay, now if we want to apply this procedure to multi-layer system, what we can do is simply taking a current, a 3-dimensional current, and restrict it so that we can restrict it to just these 2 planes. So now you have a 3-dimensional current that is restricted to live, a current operator that is restricted to live only on these planes. And so by introducing a deformation of that form, what we have is that we start from 2 completely decoupled descriptions coming from holography. So here we are summing over the effective actions that come from gravity, where, like for convenience, I called small j the response function, like the response of the operator to fluctuations. Now, indeed, these are completely decoupled, but the coupling will be provided by this double trace deformation, where indeed our current operator in Fourier space will just assume this form. And then we can integrate out of a gauge field to get our effective response function. And you can see by inverting this matrix that the interlayer response function will take again a form that is quite well known from RPA, where we have our polarization bubble coming from holography and this effective Coulomb potential. Now from this then, we can compute the drag resistivity that is just given by an integration with a thermal factor and the Q square factor coming from the vertex of this interlayer density response and the polarization bubbles. So basically, this is all to show that from holography, you can see that the only input you need to compute the drag resistivity is given by the strongly interacting polarization bubble. And first of all,
sorry, may I interrupt you? Just one quick question that I'm kind of logical jump for me here. So this formula that you're showing in the slide is not the formula for Coulomb drag. In general, response function is given by a triangular vertex.
Yeah.
The relationship between the triangular vertex and imaginary part of the polarization operator in the form you write here is possible in certain circumstances, but this is not a generic rule. So the logical jump for me here is that how this RPA that you're presenting is actually related to an actual triangular diagram that we know exists in drag. And I can give you multiple examples when this formula would lead to incorrect predictions as compared to direct computation from the triangular vertex. So how, I mean, I just, it was just very quick transition from this holography all of a sudden to drag formula. So if you can comment on relationships, that would be useful. Thank you.
Yeah, relationship is because Okay, we think that this formula in the context of holography gives a good approximation of the drug resistivity, because what I've said before is that in holographic setting, electron self-energy only depends on frequency, or at least the behavior is dominated by frequency. So we know that like this drug resistivity formula ignores vertex correction. But here, since we know that the self-energy doesn't depend on momentum up to logarithmic correction, then we think that we can ignore the vertex correction, and that this formula for the Coulomb drug is indeed valid in this context.
Then, sorry, then I'm kind of missing the whole big point of this. So if at the end of the day, everything gets back to just RPA summation, in this RPA bubble, you have some parameter, okay? It could be your diffusion coefficient or thermal diffusion coefficient. Okay, I get it. Maybe this calligraphy approach gets some temperature dependence in the form you'd like, but in principle, you could calculate this drug resistance for, as a function of that parameter that is itself a function of temperature. And if at the end of the day everything is RPA, what is real advantage here? I'm just probably missing, the biggest point, but I'm struggling to understand it here. All of these RPA bubbles can be written down from pure hydrodynamics, no problem. You don't need this sophisticated approach. It must give you something more. So I'd like to understand what more.
Okay, what it gives more is that indeed we have a few holographic models that have been proposed as a possible candidate to describe a strange metal. Okay, and so these models are characterized by some temperature dependence of the coefficient and so on. So the point is that thanks to this coupling and this Coulomb interaction, we can check if these models do reproduce also results in multi-layer systems, like experimental results that they've computed before, or in case they would do a drug experiment, if indeed this particular holographic model give a good prediction of what the Coulomb drug resistivity would be in this system. Because like we cannot play around, and it's not just a generic model. So we have a holographic strange metal model that gives some prediction of the behavior of this coefficient.
But then it's just a question. Okay, I mean, then, so basically we can, okay, so suppose that I take this framework, I calculate through drug based on this formula, let's say, like you prescribed, your pi from previous slide contains some parameter, which is D or something. And let's keep it as general. We'll just keep it as it is. So your drug would be functional of this parameter. So that's it. So then whatever you assume about the temperature dependence of this intralayer object should give you temperature dependence, correct?
Correct.
Yeah, but again, I probably not seeing, not the advantage, probably not the right word, but the conceptual maybe advance here. Somehow I thought that it could give you a more general expression beyond the RPA that we know. That's probably something that I thought might happen.
It gives them, well, I mean, what is good is that in this holographic model, this temperature dependence is fixed. Like we don't, it's not just a free parameter, it's fixed by the model. And
sorry, what do you mean fixed? I mean, you in a couple of slides, you said you want something. So you enforced some critical exponents to be of a particular form. that enforces you to have, as far as I understand, the temperature dependence of the desired. So it's not something that it is fixed. I mean, you fixed it. Let's put it this way. So you fixed it to a way that you at least, I don't know, let's say match a desired resistivity or something, and then you proceed.
Exactly, but when this, because I fixed it and I think this particular holographic model that has been proposed indeed as a model of strange metal. But then what I want to see is if indeed this is a valid model for a strange metal or not. And we can do this by compare it to our experimental results. And since we have experimental results in multi-layer system, this could be a way to basically rule out some of the holographic model or see that this holographic model indeed do relate to experimental strange metal.
I tend to interfere as observer. I think that Alex has a completely valid point, right? That you basically could look at your pi as you get it from holography. If you logically parameterize it, you will know about the diffusivity in essence out there. And then you could use that just in the standard RPA style computation to compute the drag, right? So the sort of RPA part is not adding anything beyond RPA. It is literally RPA and it's alternative condensation, blah, blah. It's just, you know, a rewording that you're doing in RPA. So that, I think that's the issue. And of course, you have a point in there that the polarization propagator of the strange metal is a bit different from what you would get in a Fermi liquid, blah, blah, right? And that you like to relate to experiment. I think you're both right. It's just this weakness, right? That holography is not really, is really engaged. It cannot quite handle, you know, genuine Coulomb interactions, blah, blah. And all you can do is, you know, basically do the same standard tiny dependent fields, also called RPA, by coupling in by hand electromagnetism in the boundary. And that's what you're doing in essence.
Yeah.
Right. So it's okay. You know, there's a wrong about it, but Alex is right that you could basically just do it very phenomenologically. But you only need the
Yeah, that's more or less what I was trying to say.
Yeah, it's completely valid.
Okay, yeah. But indeed, what I'm trying to say is that there is some information in this polarization boundary in this pi. Indeed, it's not.
Yeah, but you basically look at that phenomenologically, right? I have this or that long wavelength behavior is also set by long wavelength behavior of my strange metal. I don't really need to do an explicit holographic computation, right? I have done it once and I could parameterize it and use that data, right, to do the RPA computation for the drag. That's it.
Yeah. Like this was a bit to show how
absolutely
RPA next to holography in the sense that it's all consistent that by introducing this double trace deformation, even for multi-layer systems.
You know, overstating it. It's sort of well understood. So double trace is very interesting when you're dealing with a pure CFT, right? Because it's basically saying I can relate an IR CFT to a UV CFT, but then you go to a finite density. And it's just another way of saying I do RPA in a boundary. In other words, it's just mimicking the effect of, you know, treating the longest Coulomb with time-dependent Hartree Fock, of Hartree actually. I find it a bit, you know, it's a bit of a, you know, basically a window dressing thing. You said in the beginning, right? It's precisely the same thing as you get from normal RPA.
Yeah.
But so it goes around the circuit. You're both right, and I don't think it makes much sense to further discuss it, right?
Yeah, sorry, I didn't understand what.
It's very simple. You should stop this discussion because you were both right. Both Alex. That's it.
Indeed, one was just a way to show a consistency. It wasn't like saying that you get something totally different. And yeah, and just moving on.
here it is, right? This is basically your hydro expression, and as far as I understand it, right, when you compute holography, you get numbers for your curly T's, blah blah, right, and then you can basically use relaxation, ain't it?
Yeah, exactly, because
That's what Alex was arguing about.
And maybe I could add. I mean, this is only the very low temp. I mean, he will show later that you also need beyond hydrodynamics, right? So I mean, it's not only hydrodynamics. So that's why what Alex is saying is not completely right. I cannot completely put everything in the coefficients because the whole response function is more than hydrodynamics.
Yeah, of course, but you know, it's basically like you.
Sorry, excellent.
Wait,
But what's more, I was exactly asking about this. What exactly is beyond? So I'm.
Well, he'll explain.
Alex,
Let him finish the talk.
This is so senseless. So from holography, you get an interesting pi. Everything else is RPA, and that was your question. Yes, there's nothing beyond RPA here, except pi is coming from holography.
Yes,
that's it.
That's true.
That is
That's
the question,
true.
Alex, and this is the answer.
Yeah, but the other thing is that pi is more than hydrodynamics. That's what I'm trying to
So
say.
you get from holography, you get pi, and everything else that follows is RPA, right? That was
Yes, I agree with that.
that is true.
Just trying to shortcut the discussion because everybody agrees, you know, at the end of the day.
Yeah. And indeed, so let me go quickly through hydrodynamics, because when we get to the non-hydrodynamic part of it, it's more important. So we know that energies and momentum are much smaller than the Fermi energy and momentum, respectively. Even our holographic pi is described by this hydrodynamic model that contains in the sound mode and the diffusive mode, where all these D are the diffusive coefficient of the sound mode of the diffusive mode, and these D's that do the weight. And as I was saying, the holographic model gives you a prediction. Okay, so first of all, when if we simply take that hydrodynamic form and we take a system where both layers are the same, so they are fixed at the same density, then we see that the integrand in the drag resistivity formula I showed before contains 3 modes. And one is the low energy diffusive mode, and then we have 2 plasmon modes, an acoustic one that is linear and an optical plasmon, because in this case we just have the 2 layers. So we simply have out of phase fluctuations, and then you can think that if they're out of phase, it looks a bit like a neutral system. So the long wavelength fluctuations, so that the response will be linear, and then we will have one that causes a square root of momentum, as in the 2-dimensional case, and those are the in-phase fluctuations. And what I was saying is that our model, the holographic model, basically predicts the dependence on temperature of these coefficients. And in particular, they can all be determined for the background. And with our the speed of sound, but said has to be determined numerically, it's around 0.76 the Fermi velocity. And we can also find numerically the compressibility. And by doing a hydrodynamic analysis, we will see that the diffusive peak that has as a width that is linear in temperature, and you will have a peak height that causes T squared. And so we can try to think what kind of temperature behavior we will get from such a model. It turns out that at very low temperature, then the temperature behavior of a Dog resistivity is dominated by this diffusive mode that causes T to the fourth, and it depends also on the interdistance layers, 1 over L to the fourth. So here in this plot, I show what is the hydrodynamic result. It's very low temperature, and you see that indeed it goes. So we plot it as drug resistivity over temperature to a third to show that the relationship is linear. And the dashed gray line over here is what we will get if we consider only the diffusive mode. While if we consider the full hydrodynamics model, then we have the temperature dependence is still determined by this T to the fourth power, but is of course bigger than only considering the diffusive mode. Okay, and this is all the hydrodynamic part.
So sorry, I just understand the statement. I'm a little unsure about the language. So you say low temperature and at the same time hydrodynamic. Could you quantify what is low temperature is for your hydro description?
Oh yes, this is a very good point, because it turns out that in holography, even at very low temperature, we have a hydrodynamic behavior where the hydrodynamic scale is set by the density. So as long as we look at
but density is Fermi energy. This is the only then scale, correct?
Density is the density of this strange metal system. So it's
particle density, I mean.
Yeah, it's particle density.
Yeah, so it's Fermi energy at the end of the day.
No, it's not. There are no particles. There are no particles. I don't quite get it, because it should be always omega over mu, and mu takes all the Fermi energy.
And
so it knows about somehow, you know, Pauli pressure, right, Fermi pressure, and that kind of stuff. But you should not think that there's a particle system out there, you know, a free particle system that literally knows about the Fermi energy. I find it a bit confused, right? So the bottom line is that when you do your groups or conformal to Oras to metal, you're completely right that as long as frequency / temperature is small compared to the chemical potential, right? That's a necessary condition to find this behavior. The other one is, yeah, when you look DC, right? Because when you go to the optical response, the important quantity is frequency divided by temperature. Right, so the cutoff for the hydro is actually temperature. That's just the microscopic scale. That's generic. And when you do DC in that regard, you're always satisfying the condition. Omega is frequency here, or what?
Yes.
Yeah, so these are the general rules. I know them really. I think this answers the question. Yes, it's basically a chemical potential, right? That you can take very large.
Yes, exactly. And
that's it. So at
very low temperature, you have this zero temperature hydrodynamics. Also, there was a paper, I think the first paper describing this was by this paper by Davidson, where you find that in holographic system, at very low temperature, if you have a scale set by the chemical potential, and yeah, in this case we are working at fixed density, then even at very low temperature, you are still have a hydrodynamic description of the form that I showed before.
So once again,
so the bottom line is that you basically determined by the throat of that conformal to Oras to a black hole. And that determines the scaling behavior of everything, and that's remarkably robust, right? It extends to a rather unreasonably high temperature, right? So when temperature gets nearly of order of mu, you still have that linear resistivity, blah blah. It's just a pleasant strange metal in that regard, right? It's a pretty robust thing. What I would think is really the kind of empirical meaning here, that you have to assume that you have hydro, right, in order to get this particular temperature dependence.
Yes, exactly.
Right, and when you would measure the drag, you know that resistivity goes like linear in temperature. You measure this Coulomb drag, you will measure it like going to t to the fourth. I guess you would have kind of a direct evidence for an hydrodynamical behavior. Is that correct? It's a big deal, right? In cuprates, we don't know whether there's hydro or not.
Sorry, what's your question?
Kinetic theory of a kind that could produce a linear resistivity. It's not easy, but you can figure out things. I presume you wouldn't find this t to the fourth behavior. Somehow it knows about that you have hydrodynamical modes, right? That there's the diffusivity and all of that. Yeah, I mean, this is the big deal in this whole game, right?
I think Jan is right. So the diffusive mode alone gives you t to the fourth, basically.
Yeah.
Right, and there's no diffusive mode of this kind, right? In a kinetic system, right, where you don't have moment conservation ruling the d by r.
Yeah,
Okay.
it's a diffusive mode, but it should be linear in temperature, the diffusion constant.
Yeah.
Okay.
Right, and you know, the resistivity in a kinetic metal, the normal Ohm's metal thing, has really no clue about the diffusivity of the hydrodynamical kind. Okay, just think about it. I would say just continue.
Okay. And yeah, but then this is indeed results for some very low temperature, and if we move towards higher temperature, then we can use holography in this case beyond the range of validity of hydrodynamics to give an estimate of a drug resistivity at room temperature. And the way we did it here is that in general, the problem with holography, or the problem in holography, when you compute the spectral function, this always has in front some unknown coefficient that is related to this large unlimit. Basically, this coefficient contains the ADS radius, and so you can really compare things qualitatively, but you don't have you can get a quantitative estimate of the effect. But by introducing this this coupling called alpha, and basically this gives us another scale that will set the plasma frequency, and so we can then just take the experimental quantities that we have and choose this coefficient that will also contain these unknown coefficients such that it reproduces the experimental plasma frequency. And in doing so, we basically fix the unknown coefficient, and then we are able to estimate what the magnitude of this effect is. And this is what we did here indeed. And so in this case, since we are outside of this hydrodynamic regime, then the temperature dependence is not really that interesting because it's dominated by the thermal factor. But the interesting part is indeed is that we can give an estimate in terms of actual ohm, in this case milliohm, of the drug resistivity at room temperature. And we find that it is indeed of the order, it is comparable to some electron system, and we then wish that this can be measured in experiment in real cuprates, strange metal. And yeah, so with this, I'd like to conclude since I'm also running out of time. And basically, the message I wanted to give to you is that by including an effect of Coulomb interactions in holography, right, indeed, it's just done by simple RPA in the end. But then we can play a lot more with some toy models of layer cuprates, and this gives us the opportunity to better compare theoretical prediction from holographic model to some experiment in cuprates, and in particular, it would be really interesting if future experiment could indeed measure this drug resistivity and see if the proposed model for the holographic strange metal do indeed give sensible results for this drug resistivity. And also, it could be interesting if we would also look at the temperature dependence of the acoustic plasmon in the experiment they did with inelastic X-ray scattering, because this can give us further insight in which holographic model can actually be used to describe the real strange metal. And with that, I'd like to thank you for all your questions. And of course, if you have more, I'll be glad to try to answer.
Yeah, thanks, Enea, for the talk, also with a lot of discussions. I presume there might be more questions. So if you have questions, please speak up.
Yeah, I just, as a take-home message for myself, so for this last point, so acoustic plasmon lifetime, so what is the prediction of the holographic model? Is it linearity or what is it?
Yeah, it is linearity indeed.
And what is the Q dependence?
The Q dependence, wait, I will have to check again, I'm sorry, because I did, because in the past few months I was focusing on the Coulomb drug, so I don't remember, but
but all partially related. So from this form of the polarization operator that you obtained, I mean, in one of the slides you showed how the velocity, or I mean, how the real part of the spectrum depends on the parameters. I wonder, so when you calculate the drug, does this imaginary part, the width of this plasmon peak, it does enter into your formula at the end of the day, correct, for drug resistance? So basically, let me rephrase, does the width of the plasmon peak determines the magnitude of the drug?
Yes, because the magnitude of the drug at room temperature is actually like the main contribution comes from the plasmon peak. So indeed, it does determine, like it doesn't determine the temperature dependent.
Sorry. If you go, can you go to the formula where T4 was present? So maybe previous slide. Yes. So in this formula, in letters, not the T4, but this kappa D. Sorry, I was not able to so quickly track all the factors. Which one of these factors comes from the width of the plasmon peak?
Let's say at low energies, indeed, in the end, the plasmon peak will be determined by a combination of this factor, but this is only valid in the low temperature hydrodynamic regime. Okay, so here, this description is not valid anymore. So when we compute the magnitude of the drug resistivity at room temperature, then like all the assumptions we made about the low temperature behavior of these coefficients are not, but in the sense that we are in a regime outside of the range of validity of the small t expansion of those coefficients. But they will still be.
I'm not asking about the T dependence. I'm just asking, so if I close my eyes in T4, just look at the formula itself. So this curly D, chi, is which letter here, if any of them, comes from the imaginary part of the dispersion curve for the plasmon. So you showed in a couple of slides before that acoustic and optical plasmons, their dispersions for real parts, so square root of Q and linear in Q. But each of those lines has a width.
Yes.
And I'm asking which parameters that define the width enters into this formula for drag. This is what I'm trying to connect.
Okay, okay. Yeah, it will be all of them in the sense that the diffusive coefficient as well as these will enter in the imaginary part.
Mm-hmm.
It's a combination of all of them.
Are there more questions? There don't seem to be immediate questions, so I would like to thank Enea again. And I would also like to advertise that in 2 weeks we will have Andy Mackenzie from Max Planck Institute in Dresden, and he will speak about new developments in experiments. And yeah, I hope to see all of you then. Have a good evening. Bye.
Thanks again. See you.